Is that where it needs to be? We'll do that. Move that to that corner. A volume check. Cool. We're about 1 minute before, right? So I get to. Why not? I saw this fun video. It was 1 minute and 3 seconds long. You're not going to hear any audio, unfortunately, in this baby goats in pajamas on YouTube. Um, I hear the audio in my headphones, and um, the audio is actually part of the recording as well, but not you don't hear anything. But I mean, whatever, baby goats in pajamas. Why not? Ah! Okay, good times. I'll pause that, put that back over here, move this around, and hope that was a good distraction to the start of class. Okay, yeah, we're 16 seconds in, right? So I can start. All right, just the reminders first. Quiz open today. Please complete it today if you can, tomorrow if necessary. And just as a reminder, the turn-in method is through Gradescope. There is a response due tomorrow and homework due Thursday. We're looking at a new section. So this chapter 5, at least the way this handbook is organized, what you had noticed, I hope, was we did kind of dealt with the methods of proof, and we've been kind of reinforcing that all along. And don't worry, there'll be even more reinforcement of how do we prove a for all, for instance, again today, right? The main ideas come up again, but uh, from like the moment we started talking about proving and using, and then we talked sets, and sets naturally led into relations because relations are a special kind of set, and then functions is a special kind of relation, and then an application of functions was this thing about cardinality. We've told this story that's kind of been unbroken, like that each thing naturally led to the next thing. We now take a break, right? So I say that to kind of echo something that came in the email yesterday, is that we've been climbing up this hill, and this, it's been steep. I get it, right? And now we start this topic that's really kind of rather new called induction. It doesn't require a lot of what we've done. Kind of, we just bring it way back, way back. So that there's something really nice about that, in that this story related to induction could have been told, say, like before the break, but it would have just if we told it then, it would have kind of interrupted the bigger story. So I decided to put it off until about now. The other key thing to say about that, and I was trying to hint at that in the email, is we have hit with what we did with cardinality and, well, functions, of course, right before that. What people would in this class universally agree is the most challenging, most difficult part of the class. So there is, I would admit, there is a very clear most difficult thing that we do. I'm not trying to say that everything we do here is easy either, okay? So if you don't get something right away, okay, but that's the thing with anything that's new, right? So I'll still ask you to be patient with yourself as we learn new things, but I think with this topic today, like, it might be a little confusing today, but then you just look at it again 2-3 days from now, and you'd be like, oh, okay, right? So on a cognitive level, the stuff with the cardinality, people would generally say that that is the most challenging thing, and on some level, that's reason to celebrate, right? What I'm trying to say is, it'll smooth out. I'm not saying there's no bumps at any point for the rest of the semester, but it's nice that we don't end on the hardest thing, right? It's nice that there's kind of we've got 3 weeks, and so there's some time for that stuff to settle and for questions to get asked and this kind of thing. So today, um, this is our setup. We're going to use P of n. This is a predicate. Let P of n be a predicate. Um, and remember that that's it's kind of like a function. We have avoided calling this thing a propositional function, which some of the books tend to call it, because I didn't want to confuse it with function like we think about. But the idea here is that n is an input of some kind and has to come from a universe of discourse. And then once you plug in for n, you're supposed to get a proposition, something that's either true or false. So suppose you have to. So not only do you have a predicate, but suppose that the setup is. Suppose you have to prove for all little n in set of positive integers, p of n. So let me box that. Let's say that this is what you are asked to prove. And we've had to prove things in this general format for all, placeholder variable in some set, and then a predicate that appears after the comma. We've had to prove in this format before. The most common method, right? The most common thing, to prove when you have this setup is, you pick something, an arbitrary n in this set, and then you try to prove p of n. But sometimes you get stuck doing that. So here's a new method, so this alternate method, a common method to prove this kind of statement. So what do I mean, first of all, before we dig into it? What do I mean by this kind of statement? So first, the features about this kind of statement is there's a for all. The n doesn't matter, like what letter, because it's a placeholder variable. But the key other thing is that the universe of discourse, the set that appears here, is set of positive integers. And then beyond that, well, you always grammatically have a predicate anyway. So those three features, right? If you've got the for all, you've got the set of positive integers, you've got a predicate. Then here's a common method. So 2 steps. Step 1, you prove p of 1. Right? So once you plug in n is a specific thing, p of 1 should be a proposition. So true or false, but not both. So what's being written here is grammatically correct to say prove p of 1. Okay. And then second, what you do is you prove, and I'll change the letter here, you prove for all k in positive integers, if p of k, then p of k plus 1. So what we're doing is proving this for all up here that's boxed into a two-step process where we prove kind of one little fact on its own in part 1, and in part 2 we prove another for all statement. So proving one for all statement up here by proving a different for all statement, and then up here in step 1 this statement that's not a for all statement. So it seems a little strange, but why does this work? I'd like to convince you that this process works before doing anything else and looking at examples. Why does this work at all? So the thing to do is, it's important to note that the thing that we were asked to prove in the first place, it's in the box up there. I'm going to rewrite it over here. For all n in positive integers p of n, that this, if you really write it out, this just means if you expand it out. Remember, a for all is it's like a repeated and, right? So this really means if this has to be true, if p of n has to be true for every n in positive integers, you really mean p of 1 needs to be true, and p of 2 needs to be true, and p of 3 needs to be true, and p of 4 needs to be true, and this goes on forever. ... That's what this boxed statement over here really means. So why does this method up here actually satisfy this at all? Well, let's say it this way. So I'd like to say part 1 is just to prove, as it states up here, to prove p of 1. So that takes care of this part being true, that first underlined thing. But that, just because p of 1 is true, that doesn't mean that all these other things are true. So then, let's say that in addition to proving p of 1, let's say we're successful. We have a proof of, say we're successful proving for all k in positive integers. If p of k, then p of k plus 1. Let's say we end up proving this statement. As it's suggested up here, that this, for some reason, seems like a common method that should work out. Well, if we know this box statement down here is true, take a look at it. If we know this is true, it starts with a for all k in positive integers. So how do we use a statement that starts with a for all k in positive integers? This is a question for the crowd. Make sure we're in this together. An unmuted mic or a typed response to how are we going to how do we use a statement, like say we've already proved this, so then how do we use this? Use a statement that starts for all k in positive integers. Okay, let k be arbitrary as if you're going to prove the statement. But let's say we're already successful having proved this to be true. Don't get me wrong, up here it does say prove, and so you would have to prove that statement, but I'd like to say we've already proved it. So if let's say we already proved this statement and know this to be true. If we know this box statement already to be true, how would we use it? So let k be arbitrary if you need to prove this statement. But let's say we've already proved it. How do we use this statement? How do we use a for all statement? We need an element in positive integers, yeah? Okay, use the fact that one, yeah, and so, these two comments kind of work together here, right? So in order to use this for all statement here, we need an element in the set of positive integers, and it's come up already that 1 is such an element, right? So for example, 1 is known to be a positive integer, and so if you combine this with this, you end up with the fact that if p of 1, then p of 2, right? That's this part over here underlined in green, just plugging in 1 for all the k's. But see, the thing is, 1 isn't the only element that we know in this set. We also know 2 belongs to this set. So combining, combining the fact that 2 belongs to this set and the for all something in positive integers, we end up also learning if p of 2, then p of 3. So check out what this does for us. We already knew p of 1 up here. So then, so from this fact right here, and knowing p of 1 right there, we get p of 2, right? Modus ponens. And then knowing this implication, p of 2 implies p of 3, well, we know p of 3, we know p of 2, so p of 2 combined with p of 2 implies p of 3 gives us p of 3. And it goes on, right? So since 3 is a positive integer, we know that p of 3 implies p of 4. And knowing that, together with having p of 3, this gives us p of 4, and so on and so forth. Right, so there's an infinite number of uses of modus ponens that's happening. In fact, I could say now a countably infinite number of uses of modus ponens. Okay, so I'd like to sort of provide a cartoon analogy to what's going on here. The idea here is this is like dominoes. Right? So if you've set up a bunch of dominoes and you're gonna, hit a domino and then each one's gonna cascade and then the next one's gonna fall over. The part 2, we look at this statement that's still boxed up here. For every k in positive integers, if p of k, then p of k plus 1. It's not a perfect analogy, but I want you to have this cartoon idea that this proving this part to be true. If you know this is true for all k in positive integers, if p of k, then p of k plus 1. What is this statement? What is this like, right? So I want this step right here. I want to think of this as saying this is like saying that consecutive dominoes are set up close enough to each other right? So this is trying to say domino 1 is close enough to domino 2, Domino 3 is close enough to domino 4. Domino 98 is close enough to domino 99. And by close enough, I mean like, so that domino 98 falling would cause domino 99 to fall. Okay, this part right here, sorry to do this, is called the induction step. And then part 1, so fine. Like, if you just set up a bunch of dominoes so that they're each close enough to each other, that doesn't make anything fall. That's just a setup. But something else has to happen. You gotta push that first domino, right? In order for anything to happen. That part is called the base case. So the separate thing that needs to be proved is P of 1. Kind of just all on its own needs to be proved. And this is pushing the first domino then. So just at least in a general frame, I hope that this kind of helps set up what this process is and why this works. So it's sort of taking, sorry to scroll up all the way to the top here, but taking this statement that you need to prove, and instead of doing it the traditional way, I mean, do it the traditional way if it works, but the whole point now is if you're stuck proving this the traditional way of picking an arbitrary positive integer and then proving P of n, this gives you a new way to do it, and it's structured building off of using and proving for alls. Okay. One other comment before we get going is that this piece right there, so in this bigger statement, this induction step that's been boxed, this P of k right there, P of k here is just given a name because it's helpful to refer to it at times. This is called, it's not a formal definition for this class. I'm not going to ask you to define this. It's helpful to know what people tend to call this. It's called the inductive hypothesis. So this is helpful to have a name for it because sometimes as you're working to prove this if-then, it's helpful to refer to this P of k thing. So I think what we should do, unless there's questions, comments, or whatever, is dig into an example. Okay, let's look at the following example then. Theorem. For all n in the set of positive integers, the sum I goes from 1 to n of I is equal to the fraction n times quantity n plus 1 over 2. I'll just comment that this theorem is used in Calc 1, in our Calc in Math 207. It's not stated with the for all there, but it's in the calc book, and it's used when you first talk about a definite integral as a limit of Riemann sums, and this feature comes up. But we don't need that right now. I'm just pointing out you may have seen this before, so it may look kind of familiar. I'll just point out if you try to prove this a normal way, you would assume that you've got a let n in positive integers be arbitrary, and then you'd stare at this fact over here of, okay, if I add 1 plus 2 plus 3 plus 4 plus all the way up to n, that's supposed to magically equal this fraction. What the hell? How do I do? There's nothing that's useful in doing this, to be really honest. So what we're going to do is we will prove this by induction. Not that this sentence is required, but it doesn't hurt to have. We prove by induction. Just to clarify to the reader what we're doing, that we're not doing the usual approach. I will include a comment. Not that the comment should really be included in the proof, but just to clarify what the heck we're doing here. The text after the comma, this is the predicate. So P of n here is this sum of the first n positive integers is n times n plus 1 over 2. That's what P of n is in this example. So for the base case, there are two things we need to do. We've got to prove P of 1 first. For the base case, right, we need to prove P of 1. We need to prove. Now take a look over here in green. That's P of n. That's P of n in green. So we need to prove P of 1, meaning we need to replace all of the n's with 1. We need to prove, just write down what we need to prove. I'm just plugging in a 1 everywhere I see an n. So sum I from 1 to 1 of I equals 1 times quantity 1 plus 1 over 2. All I did was took what's in the green box, replaced every n with a 1. That's what p of 1 ought to be. So proving this, we don't need anything super fancy. Just take a look at the left side. The left side of this, the sum, let's try that again. The sum I from 1 to 1 of I just means add up things that look like this expression I, starting with I equals 1 and ending at I equals 1. So there's only one term, and it's 1. The right side is 1 times quantity 1 plus 1 over 2. This is 2 over 2, which is 1. Cool. These are equal, right? Equal. That'll do for our base case here. For the inductive step, let's just, sorry to do this, I'm going to scroll up and just grab a copy of that inductive step so that we have this right there. We need to prove this other thing here. Okay, so we must prove we want to show this. In general, I would not probably include this sentence, but it's the first time around. And normally I'd, in the class, still have the other whiteboard to point at for this. So we want to prove this statement. In order to prove a statement that looks like this, that starts with a for all, now we're proving we should let k in positive integers be arbitrary, right? So to prove this, so let k in positive integers be arbitrary. Okay. Now what we, having done that part, like as usual, then we need to prove that statement right there, this implication. So we should assume the first part, and then we want to prove the second part, right? So what I'm going to do is, we need to assume p of k. So we're going to suppose. Now what's p of k? Well, go back up. Just sorry to scroll one bit. Up here in the upper right, in that green box is p of n. So what's p of k? All you got to do is replace all the n's with k's. So suppose that we have sum I from 1 to that n is replaced with a k of I equals, on the other side, k times quantity k plus 1 all over 2. Suppose that that's true. We want to prove, so right, this is proving an implication, so then we want to prove the conclusion part, the p of k plus 1. So we need to prove okay, then take a look at the green box up here again, and we're going to replace every n with a k plus 1 now. So we need to prove sum I from 1 to that n up here gets replaced with a k plus 1. K plus 1 of I equals, every n gets replaced with a k plus 1. So there's a k plus 1. We better put that in parentheses. And then n plus 1 should be a k plus 1 plus 1, but I'm just going to write a k plus 2 if that's cool with everybody over at 2. All right. How are we doing so far? I want to see if we're okay with, we've got positive integer k that we don't have control of. The reader of the proof picked something. We don't know what positive integer they picked for k. We're going to say that this statement is true based on whatever fixed positive integer k that they've picked. And then we need to prove this statement down here. So we've now picked through all our, how do we prove a for all, how do we prove an implication. Now we're going to be down to just some algebra, to be really honest. But I want to pause. Are we doing okay? Can I clarify anything before we start proving that? We're going to use this equation here to prove this equation over there. I'm going to just take a moment, see how we're doing. If you've got any questions. So in this specific proof, this equation that's right after the word suppose is our inductive hypothesis, just to connect it back to that naming. So how are we going to apply that? So this fact that we suppose is something we know is true, how is that useful at all? That's what we need to figure out, because if we don't use this, then we're not, something's a little off. Well, take a look at the thing we want to prove, and as usual, I don't like to start with notation, so we'll just write the word note, and I'll start with the left side. You can start with the right side of this as well. So I from 1 to k plus 1, sum of I. Now we are eventually going to show some work here and lead to this fraction that's right there. So I'm going to erase, that's our goal right now, right? Now here's the thing. The sum, this requires a little bit of like thinking about what sigma notation truly means, but the sum of i's going from I starting at 1 and ending at I is k plus 1, you could write this as the sum I from 1 to k of I, and I'll use some parentheses just to clarify, plus there's one more term, and that's when you plug in, so k of the terms, there's a total of k plus 1 terms here, and k of them are written right there, but there's one last term, which is when you plug in k plus 1 for I, and that last term is going to give you just a k plus 1. Let's pause there. Are we doing okay? It's a kind of common method of dealing with sums, so usually infinite sums in Calc 2, that we're just doing a finite sum version of this where there's k plus 1 terms total, and we broke it down as the first k terms and then the last term. The last term is just a k plus 1 because the kinds of things we're adding up are just of the form I. Are we okay with this step? What do we do now? What should we do now? Who's got an idea that, what could we do? Why would we even bother writing this thingy like that plus that? Where are we headed now? Who would like to share an idea? Maybe. Any thoughts? What could we do with this part right here? Simplify the right side of the equation before the note. Okay, yeah. Yeah, and how will we simplify this? So the hint is built into this thing that I just boxed in green. Is there another way that we could write that? Remember, we have this inductive hypothesis. Yeah, that sum, yep. That sum is just the first sum, but with just going up to k. And take a look. So this part, let me underline this part in blue right there. That's up here. Remember, we had supposed that that is equal to this fraction. So the three places I've underlined things in blue, they're actually all equal, right? So I can replace this sum I from 1 through k of i's with k times k plus 1 over 2. I just made a replacement. Finally, for this to truly be equal, though, we still need to copy down k plus 1, which was there before. Now let's simplify this. How about k times quantity k plus 1 over 2 plus, you know what? That k plus 1 doesn't look like a fraction. How about 2 times quantity k plus 1 over 2? So all I did was I took what was there, I just multiplied by 2 on top and bottom. And then, now that we have a common denominator, we could write this as 2. So it's really technically, I guess, this thingy plus that thingy, but since they both already have a k plus 1 factor, I'm going to factor further and call this a k plus 2 quantity times k plus 1. And take a look, that fraction right here, That's what we wanted. It's just the factors in the numerator written in a reverse order, but it gives us what we want. We have what we want. So we've proved the inductive step, right? So we assumed this. We used that to prove this. The proof of this is what's down here. And so by induction, we have a technically what's considered in the math community a good proof of, for all n in positive integers, the sum I going from 1 to n of I is equal to n times n plus 1 over 2. We have what's considered a complete proof of this, even though we didn't prove this for all in the traditional way. So we're done with this one. And before the next one, let's pause and find out if we have any questions that can be answered. Could you explain again how you did the sum of k plus 1? It's not, okay, so yeah, I think it's harder to just type it, but it's not the sum of k plus 1. It's the sum of i's, as I starts at 1 and I ends at k plus 1, right? So just to clarify what this means, right? This is maybe like a review of the summation notation. I'm going to make up, it says up here, let k in positive integers be arbitrary. Maybe the reader picked k to be 3. So let's just, as an example, we're outside the proof. Let's just say that the reader picked 3. Then what is sum I from 1 to k plus 1 of I? Well, if I replace the k with a 3, it's sum I from 1 to 3 plus 1 of I, or I'm going to do every little gory detail. Sum I from 1 to I equals 4 of I. This means 1 plus 2 plus 3 plus 4. Right? So the point is, then the sum of i's, things of the format I, starting at I is 1, going up to k plus 1, what's happening right here in the example form is to group together these first 3. So what's in blue, underlined in blue here, that's like that part. It's just written in summation notation again. And the final thingy, this 4, maybe I'll underline this in red over there, that 4 was k plus 1, right? So if k is 3, I shouldn't use the same color. If k was 3, then there's a 4 over here. That 4 is k plus 1. So all we're doing is we're taking this sigma notation, which has a total of k plus 1 terms, and just breaking it apart into the first k terms, and then the final term, which is the k plus 1 term. And why are we breaking it in that format? It gives us just even the chance or hope of using the inductive hypothesis. The inductive hypothesis was talking about when you add up the first k numbers, you get this fraction over here. Does that help clarify what was going on there? Okay. Other questions? So I think sometimes what happens in this kind of question is people may need to review some sigma notation. So I know this class, you have perhaps noticed, doesn't use a lot of things from the past in some sense, like barely any calculus or whatever, but even in Calc 1, people experience some Riemann sums and dealing with sigma notation. So there's unapologetically, at least, there's some of that stuff. And okay, so I will then make the following note as I have it in my notes, is that when we say induction, so in everyday life, when people say the word induction in everyday, what they usually mean is, induction usually means just noticing a pattern. And making conclusions. Okay, and I use this word like this in everyday life as well. In a math class, that's not what the word means, right? So I'm just saying, look, every day go out there in the world, say the word like this. But in math, induction does not mean this. So in math, induction refers to this process that we're talking about, this two-step process of base case and inductive step. So this is just a place to be a little careful. I say this because when we talk about this area of induction, sometimes what people do is they'll go like, oh, I don't need to do anything precise. I'm just going to like say that I see a pattern and then call it a day. But that's not what's going on. This is very precise stuff that we're doing. In fact, before looking at one more example, I want to, if this will show up here, I created this little handout, and you'll find this in the handbook anyway. But the whole point is, how does induction work? You start with a predicate that's been provided to you, and the setup is that you want this given predicate to be true for all positive integers. And there's this part down here. This part's drawn in kind of more bold. Like if you end up, based on just the predicate alone, proving P of 1, that's the base case, and then proving that for all positive integers, this implication, which is called the inductive step. If you prove those things, then down here is this sort of generic argument that like, 1's a positive integer, so this leads to P of 1 implies P of 2, and as soon as you know P of 1, right, lots of modest ponens occurring, this ends up giving you P of 1 and P of 2 and P of 3 and all these are true, and that ends up being the final statement. This is sort of a roundabout way to prove this for all statement. So the point is, this stuff that all happens down at the bottom half of the flowchart down here, you don't need to prove all of this each and every time you do a proof by induction. That stuff is just kind of like granted for free. The part then that's different is you've got to provide, based on the given P of n, an argument for why P of 1 is true and why this for all statement is true, and prove that for all, the bold boxed for all statement, prove it in the traditional way of proving a for all statement. It's in fact a for all combined with an implication. So the proofs of those two boxes is specific to whatever P of n is. And so when in the math community, you don't ever have to repeat the bottom part of this flowchart. It's good for you to kind of go through it once or twice to make sure you're clear with what's going on. But people usually expect you to just do these two sort of dotted pieces right there. And so I'd like to then, let's look at another example. This is a very different kind of example, but that's kind of what I want to do, just to kind of get your experience through all this. Is so for all positive integers n, so this time it's written out, but it could have been notation, the integer 3 divides n cubed plus 2n plus 9. So the proof that we just did earlier is the classic first proof by induction. So it had to be shown. It's one that you just kind of, everybody's got to see it. For this one, before digging into the proof, I'll just comment by identifying what P of n is. I'm not expecting you to, in words, identify it in the middle of your proof or even at the start of your proof, but since we're new at this, I just wanted to identify that in this example, P of n is the predicate 3 divides n cubed plus 2n plus 9, right? So this box thing here, that's the predicate. So in other words, once you plug in a positive integer for n, then it could be either true or false that 3 divides n cubed plus 2n plus 9. But the point is, the thing boxed here after plugging in for n could be either true or false. It's a common error to say P of n equals n cubed plus 2n plus 9. So please avoid doing that. Okay? At least if you're matching the notation of what we're doing. If you want to call P of n this, okay, fine, but then the thing that I called P of n into the general framework for induction, just call it something else then. The point is, in this problem type, for some reason, people think it'd be a good idea to reuse P of n to perhaps have two meanings. Sometimes people are like, use P of n as a predicate, and then as written like this, it looks more like P of n as a function, although the domain and codomain haven't been provided. if you say that P of n equals n cubed plus 2n plus 9, what business do we have of saying that P of n is true, right? Like, the output for a function is neither true nor false. So let's be careful with what P of n means, and to just match the notation with what we have earlier, let's stick with P of n as the predicate. If you wanted to do something like this, it's not even in my notes. If you really wanted to, how about as a suggestion, if you're going to do it this way, why not create a function from positive integers to who knows what? So let's just say reals, just to be safe. Well, they'll be integers, won't they? Right? Where you do something like, you say that f of n has as its rule n cubed plus 2n plus 9, and then you can say that P of n is 3 divides f of n, if you're going to do it that way. But what I'm trying to get at is, let me circle in green that that's a number. This is a number, right? And you'll notice the issue is trying to use P of n for both a predicate and the output of a function leads to some confusions. So if that's yeah, maybe I'm over saying this right now, but the point is, let's just be clear that I want P of n to be a predicate right now. Don't use P of n for two different roles. You're going to get yourself confused and write things that are grammatically incorrect in homework and quizzes, and I don't want that to happen. Okay, so proof of this for the base case. So this common error thing, let's just cross this out in red. That was not red. So for the base case, we need to prove P of 1, right? So we want to show, for the base case, so take a look at this box thingy up here. We want to show that 3 divides, well, let's just plug in 1 for all the n's. 1 cubed plus 2 times 1 plus 9. In other words, we want to show that 3 divides 1 plus 2 plus 9. We want to show that 3 divides 12. Well, the reason this is true is, so 3 divides 12 because there exists an integer, right? There exists I don't know what we want to call that integer, y, in integers, such that 3y is equal to 12. That, namely, y is equal to 4, right? So there's not a lot happening in this because there's not actually a lot of variables in this. We're used to statements about divides having so many extra variables. The fact that we actually have something super concrete in just a number 3 and a number 12 means that to show that 3 divides 12, we just produce that other number, in this case 4. For the more difficult part is the inductive step, right? So for the inductive step, so just to stick to the notation we had, I'm going to use a k. So let's let k be a positive integer. So arbitrary positive integer. We don't get to pick. The reader of the proof picks whatever positive integer they want. We don't know, but it's just called k. And then, so remember what we want to show now is we want to show that P of k implies P of k plus 1. And sorry to do this. I'm going to scroll back up. P of n, I'll just copy this so that we have a reference copy of it down here. Sorry to do this. P of n was this, right? So we're going to assume P of k, meaning we're going to assume what's in this box, but replacing all the n's with k. So assume 3 divides k cubed plus 2k plus 9, and we want to show P of k plus 1, meaning take what's in this box, and we need to replace every n with a k plus 1. So we want to show 3 divides k plus 1 quantity cubed plus 2 times k plus 1 plus 9. Are we all okay with just the general setup of where we're headed right now? That we're assuming this underlined in green is the inductive hypothesis. I mean, it's P of k in the general story, but for this specific problem, this is P of k underlined in green. And then we want to prove what's underlined. Let me underline it here in blue. We cool with that's what our general setup is right now? So let's do this then. So since we've assumed that 3 divides k cubed plus 2k plus 9, because of that, there exists an integer. I don't know what letter I called it. I'll just copy the same letter I had earlier. There exists an integer w is what I used in my notes, so I'm going to do that. So let w equal, so not, oh geez. So there exists a w in set of integers such that 3w is equal to k cubed plus 2k plus 9, right? The underlined green phrase is what we know to be true because we've assumed it. And 3 divides this other integer that starts with a k cubed. That's what's down here, right? So underlined in black is the same as what's in green to me due to the definition. And then we're going to define let little r equal, well, I don't know what, so I'm just going to leave some space, and we're going to come back to it. Now, take a look. What I'd like to do is start with a proof of what's in blue, and the way I'm going to do it is I'm going to actually work with one side. So k plus 1 quantity cubed plus 2 times k plus 1 plus 9. And if I cube this out, I'm going to have, let's see, so k plus 1 times k plus 1 times k plus 1. I'll just spare you the details there. It's k cubed plus 3k squared plus 3k plus 1. And then if I distribute out the 2, I'll have here a 2k plus 2 plus 2k plus 2 plus 9. Okay, so there's actually a theorem called the Binomial Theorem. Sometimes it's learned in calculus. That's how I did the cubing of k plus 1 so quickly. If you want to call my work out, then just double check by doing the foiling. But what I'm going to do is, let me see here. I'm going to put the k cubed, that term first, and then I'm going to put this 2k here next, and then I'm going to put this 9 here next, and then I'm going to write the other terms that are not yet underlined. Let me actually leave a little space so you can see the underlining better. I'm going to write the 3k squared plus 3k plus... What happened here? Oh, I left out a 2k. I was distributing 2 plus 9. So let's see. I've already written the k cubed, the 2k, and the 9. What wasn't written yet? So 3k squared plus 3k plus 1 plus 2. Sorry about that. I missed something in my Thank you. Yep. Thanks for the comment, Hannah. Okay. So I was just like staring down here, and I didn't. I should look up at the comment boxes. Are we okay with what happened? I juggled the order. Now, why would I do that? Why did I underline these 3 terms specifically and decide to put those first? Is there any good reason to do this? Anybody kind of catching the motivation of why that happened? Replace it with 3w. That is, right? Yeah, so let's avoid calling that P of W though. So the P of W is not this alone. It's P of W is that this is P of W. Oh, sorry, that's not P of W either. That's P of K, right? So the point is that this right there can be replaced with 3w. But yeah, that what's boxed up here, let's just be clear. I know it's real picky, but that's P of K because up here underlined in green, that's P of K. So it's not P of W, right? It's P of K. Okay, so the point is the first 3 terms, I'll just copy this plus sign here first. That plus sign is that plus sign. So we can replace k cubed plus 2k plus 9 due to the inductive hypothesis with 3w. The rest of this stuff, we can rewrite this as 3 times, let's just write it as 3k squared plus 3k plus 3, and write this again as, if I factor out a 3 out of everything, w plus k squared plus k plus 1. I'm going to then now define r up here to be w plus k squared plus k plus 1. This is sometimes how I actually write proofs. Like I don't know what I want r to be, but I'll just, now that I know 3r, take a look. R up here is an integer, so it belongs to integers. R is an integer, and 3 times r is equal to that, right? So since we now have there exists an r which is integer such that 3r is equal to k plus 1 quantity cubed plus 2 times quantity k plus 1 plus 9. I just copied that from right over here. We actually have, so now we have 3 divides this k plus 1 quantity cubed plus 2 times k plus 1 plus 9. That was what we wanted to show to finish our inductive hypothesis. Okay, so we're done, right? So if you want to say something, you can, but by induction, we're done. Okay, so that's the end of that proof. Let's pause and see how we're doing, and see if, let me scroll up, just make sure. There's usually, again, a comment, a question of like, wait, how did you do this? How did you do that? I think then a good way to end. Now we don't have time to do another one in full, but I think it's important for me to state here. I want you to understand. I want you to like challenge yourself to dig into, understand the idea of what proof by induction is doing. What proof by induction is doing. Is like it's what's really going on, because if you really like, it should not be just a magic trick. It should be like, okay, it's built on these principles. That little handout that I projected for a moment, there's a copy of it inside the handbook as well. Like I want that to be understood, because if you understand what's really going on, then you can modify the method. That's sort of the true test of like, do we know what's happening, what's really going on? So here's an example of this theorem for all integers, but as part of the for all, it's for all integers n greater than or equal to 5. The inequality 2n squared is greater than quantity n plus 1 squared holds. Okay, so the thing is, that like this one, it's not a for all. It's not all positive integers. It's only positive integers starting at 5. So this is kind of different, right? And so we don't want to use induction the way it was originally presented right at the beginning of class. We want to tweak it just a little bit. But this is sort of like remove the first domino and second domino, third domino, fourth domino. The fifth domino is now the new first domino. That's the idea, right? So here, just to make sure we're clear about what's going on, we'll just define the predicate. P of n is the inequality. Sorry, kind of poor grammar here. Define P of n is, maybe it should be P of n to be. 2n squared is greater than n plus 1 quantity squared. Okay? And then here what we want to show, just to clarify, we want to show for all n in, I'm making up notation on the fly, but I think you'll be okay with it, for all integers greater than or equal to 5, P of n, right? And so now our new base case is we want to show, instead of P of 1, we want to show P of 5, right? So if we want to show P of 5 is true, well, let's take a look at what this is saying. We want to show, plugging in 5 for every n, 2 times 5 squared, is this greater than, question mark, 5 plus 1 quantity squared? Well, let's just simplify and note that the left side is 25 times 2, so 50, and then this side is 6 squared, or 36. So that checks out. Okay, P of 5 is true. And base case is usually real nice compared to the inductive step. That's not always true, but the base case is usually nice because there's usually not very many variables floating around because you've plugged in for n. Often a 1, in this case, plugged in a 5. And for the inductive step, I don't think I have time, so we'll probably pick this up tomorrow. But just to get you started, you can look at the notes if you want, but just to get you started, because we started at 5 here, so what we want to show, maybe I'll just clarify it now, is we want to show, and I'll use the k, for all k in integers greater than or equal to 5, if p of k, then p of k plus 1. So what we do now to prove this is, like proving any for all, we let the reader pick an arbitrary integer k, except k has to be 5 or bigger, right? So let k be in here, arbitrary. And so then now we have to, usual thing, we have to prove an implication. So we suppose p of k, what's p of k? Again, back up here, circled there, that's p of n. So we suppose 2 times k squared is greater than k plus 1 quantity squared. And then what we want to show is take this blue statement circled up here, and what we want to show is replace every n not with a k this time, but with a k plus 1. So we want to show 2 times k plus 1 quantity squared is greater than k plus 1 plus 1, or if you want to write k plus 2 quantity squared, fine. So I think because I'm a little out of time, I'm not going to do that right now, but maybe try it on your own and see if you can, if you'd like to, then look at the notes. So we'll call it with that. Don't forget the quiz. Quick question about equicardinality. If two sets are equicardinal to another set, can you say those two sets are equicardinal to each other? Yeah, though that should be proved, right? So if A is equicardinal, sorry for the abbreviation, to B, and B is equicardinal to C, then that means you've got there exists a bijection, let's say F from A to B, and there exists a bijection G from B to C, right? And both of these are bijections. The question is, does there exist a bijection, let's call it H, from A to C? And actually, believe it or not, it is a relatively short proof to come up with a bijection H in this case. And it can reference the rules for F and G, even if the rules are not known for F and G, right? So, yeah, I see your question as well, Mitch. Give me just a moment to finish this question. I will address that if you can just hang out by the podium for another minute or two. So think about, like, based on F and G, is there a way to construct a function H? In fact, how about, Hannah, I'll give you a moment to just think about it, and I'll switch to the other question, and then if you're like, I give up, give me a hint, and I'll just state what I think H could be, or at least a one word hint. And then, okay, so then let me read this question. Is it possible to make bijections between uncountably infinite sets, like R to C? Yes and no. So that's a really good question. It depends on which uncountably infinite sets, unfortunately. So this is a really good question. So it turns out that that R is uncountable, that the set of complexes is uncountable, and it turns out that these are equicardinal to each other. So R is equicardinal to C. That ends up being true. However, just because a set is uncountable, so let's say that you have, I'm already using up there A's and B's and C's, so let me just new sets, okay? Just if X is uncountable and Y is uncountable, this does not mean that X and Y are equicardinal. So uncountable doesn't automatically mean that having two uncountable sets doesn't mean that the two sets are equicardinal. What? So there are different, as sort of was hinted in a kind of a very, what's the word, casual sense yesterday, informal sense. There are different levels of infinity, and you in fact heard me mention aleph naught, right? This is the cardinality that's assigned for the set of positive integers. And aleph 1, it turns out, is what people tend to write for the cardinality of the reals. And the continuum hypothesis thing yesterday is in a sense informally is sort of like, is there an aleph 0.5 or an aleph 0.8? We don't know. Like that's not a question that we, but there is actually, there's a set with cardinality aleph 2 and there's a set with cardinality aleph 3, and these are all not equal cardinalities to each other. So like there's different levels of infinities. Now it turns out I haven't given you a bijection, but you can prove that R and C are equicardinal. Um, I guess what I need to do though is you're saying like wait, you might say like wait, there's all these other cardinalities here. I just need to point out if you take the power set of any set, so start with any set. X could be a finite set, infinite set, countable, uncountable, doesn't matter. Start with a set and then look at its power set. These have different cardinalities. So in fact, the power set of a set always has a larger cardinality than the original set. So all I'm getting at is R is uncountable, yeah, and then the power set of the reals, the set of all subsets of reals, has a larger cardinality. What is it and how do you dig into it? These are things that I don't really know a whole lot about, or I used to when I once took a class, but it's been years and these are not thoughts I think about usually. So then let me go back. Hannah asked a new question. But just to go back to the old thing, just the hint for H is think about composition. And if you just compose in a way that works, you'll be fine. Composite. Okay. So oh my goodness, so is a set of quaternions equicardinal to anything? I'm gonna be really honest. I don't know. I mean, probably equicardinal to something else interesting. Yeah, probably, but like, I'd have to think about that a little more to be really honest. So off the top of my head, I don't know. Of course, it's equicardinal to itself, but I mean, you meant something else, like more interesting, and I I'm not gonna sit around and just bullshit my way through it. I don't know the answer to it, so I'll have to check on that and kind of get back to you, or like kind of think about if there's something kind of more interesting to say that the set of quaternions is equicardinal to. So uncountable is like a classification, whereas cardinality is more like a size. Yeah, I guess that's a fair way to think of it, right? So like, there's many yeah, so I mean, and maybe the point is the definition is a definition. So any set, that's why it was phrased the way it was. Any set that is not countable, and countable is either finite or same cardinality as set of positive integers. If it's not that, it's uncountable. But this forest of uncountable, it's a wild forest out there. There's lots of things out there that are uncountable, that are just not at all equivalent to each other in size. I mean, there's lots of features in like an axiomatic set theory class that I took back in the year 2004 that I've forgotten about because I never apply these principles most of the time. Like I forget even like there's these theories of like, can you take all cardinalities and always say that one is less than the other, or can you have two sets of two different cardinalities where you don't even say that one is less than the other in terms of size? So there's a lot of stuff going on out there. I mean, a lot of things that I'm almost, there's a danger in saying too much right now because then you like want to look up all these things, but like most of these things won't make actual complete sense until after this class, and then after abstract algebra, and then a full class in axiomatic set theory. But yeah, this is a very, very strange area of math. So I hope feel free to ask other questions. I'm not trying to avoid answers so much as to say like there's this world of there's this area called axiomatic set theory. What we've been looking at, the way we look at set theory, it tends to go by the name naive set theory. And there's a world of difference in what's going on here versus there. Most of the time, thinking in the naive approach about set theory is usually just fine. But people have worked out there's reasons to like really kind of dig into the details, and it like you got to be super comfortable with all the aspects that we're bringing up in this class about proof, and sets and relations and functions and cardinality and equicardinal and all these things in order to start really digging into axiomatic set theory. But it's a subject area out there kind of on its own. Very interesting stuff. And in fact, one of the things I want to do once the semester's over, right? Like once it's not, like, I don't want anyone to stress about it, is I was going to write up a couple little like one pagers of like, hey, if this topic in class was interesting, you might want to read this, because we lost a week of class, right? So I plan on, if I can, get organized like late May, sending out things to people saying, "Hey, class is over. You already have your grade, but if you want to do a little extra reading and this or that, some pointers." So any other questions now though that I can? Is AST a post grad class? Um, no, not necessarily. I mean, I think it depends on the university. I took it as an under. I took axiomatic set theory as an undergrad. Um, the professor I took it from has since passed away. She was amazing. She used her own notes, and didn't. She just came into class every Monday, Wednesday, Friday, dropped her windbreaker down on the table, said "Good afternoon." And last time we were in the middle of this proof, and she had no notes. Like, just, oh my god, it was one of the best classes I took. But there was an assigned book for the class. It just wasn't, she didn't really follow it. She just like had it all in her head, and it's like this is the way to organize it. And the way she did it was way better than the book, to be honest. The book, though, it was by Herbert Enderton, and I think the book title was Elements of Set Theory. I wouldn't dare crack open the book right now until this semester is done, right? Because it'll things will get confused. But like in principle, as soon as this class is done, one could, in principle, pick up a book on axiomatic set theory. I think the better thing to do, axiomatic set theory, it doesn't really require any abstract algebra, but you end up thinking a lot in the same way like you would in an abstract algebra, or like, now that we have it, like a topology class. So probably after this class, better to take either abstract algebra, our 411, or topology, which is our 415. Take one of those first, and then go pick up a book on axiomatic set theory. That's probably the best way to approach it. But yeah, it can be done as an undergrad. It's very, very, it's a certainly difficult subject area. I think more difficult than abstract algebra or more difficult than topology. But I don't know that I'd call it a postgrad class. There are definitely postgrad versions of it, grad school versions of it, but it's been taught in undergrads. One of my office hours tomorrow. Tomorrow's Wednesday, so 1:10 to 3:10. Okay, sounds good. I will stop the recording and